So, now that we know how the planets move around the sun, let's see if we can understand why this is. So remember what Kepler's laws were. Kepler's laws were laws that he came up with, and he used the data that had been collected by Tycho Brahe over a long period of time. His laws, because they were based totally on data without any physical explanation, are called empirical laws. To be honest, Kepler could not offer a physical explanation for why the planets moved the way they did. All that he knew is that the data told him that this was how they moved. We will see that Newton was able to explain the motion of the planets through his laws of motion and gravity. So, there are some terms that we need to understand before we move on. For instance, what is the difference between speed and velocity? Well, in our everyday language, we probably use these terms interchangeably, but in physics, they're not exactly the same. Speed just means how fast something is going, while velocity actually means how fast it's going and what direction. So, speed is just how fast, velocity is how fast and in what direction, or another way of saying that would be speed and direction. So, Newton's first law of motion. Newton came up with 3 laws of motion that just in general tell us that there has to be a force acting on the planets. His first law of motion is that an object in motion will tend to stay in motion, and an object at rest will tend to stay at rest. Both of these things are true unless that object is acted on by a net force. So basically what we're saying is that if something is rolling along in a straight line, the only reason it will come to a stop or veer off is if a force acts on it. Similarly, if an object is just sitting there motionless, the only way it'll come into motion or start to move is if something acts on it, a force. That's what Newton's first law was saying. Sometimes we call this the law of inertia because inertia refers to an object's resistance and its change in motion. So, acceleration is the change in velocity over time. Keeping that in mind, which picture shows a car that's accelerating? Well, let's see. The first picture, we would say, oh, definitely, that one is accelerating because it goes from 30 kilometers per hour to 60. So the speed change to us means acceleration. Similarly, we probably recognize that the bottom one is also acceleration, although we might call that deceleration because the car is slowing down to a stop. It's the middle one that we might not be familiar with because of our lack of knowing what the difference is between speed and velocity. This middle picture is actually also accelerating because while the speed of the car is not changing, its direction is changing. And because of that, its velocity is changing, and because its velocity is changing, it's accelerating. Now that we know that, we're ready to move on to the second law of motion, which explains what happens if a force acts on an object. Remember, the first law explains what happens when no force acts on an object. So now in the second law, we explain, okay, now if there is a force, what's going to happen? Newton said that if there is a force, that force will cause an acceleration. The acceleration will be directly proportional to the force, that is, bigger the force, bigger the acceleration, and inversely proportional to the mass. Larger the mass, smaller the acceleration, and vice versa. So, if a planet travels in a circular orbit without speeding up or slowing down, does it have a force on it? Well, we already saw that the car that was traveling in a circular path was accelerating. So it stands to reason that because this planet would have an acceleration, then it also would have a force acting on it. The answer is yes. So, if we think about the planets traveling in their circles, it can be similar to this ball on a string. As the planets go in semicircular orbits, we can understand that there must be some force holding them into that circle. Because we know, according to Newton's first law, if that string breaks, the planet will fly off in a straight line in the direction it was moving at that time. So simply using Newton's first two laws, we can postulate that planets only orbit in those orbits that they take because there's some force acting on it. Furthermore, we can postulate that that force is towards the center of their orbit or towards the sun. Newton called this force the force of gravity and said that the force would be proportional to the two masses and inversely proportional to the distance between them squared. Now, that force of gravity exists between any two objects with mass, but because this number right here, big G, is a very small number, the force of gravity is actually very weak. So it's only really an appreciable force when one of the objects is very large, such as a planet. That would explain why we don't all feel a force of gravity attracting us to each other, because our masses are too small to give an appreciable force. So, how does the gravitational force between two objects change if the distance between them triples? Well, here are our choices. Does the force increase or decrease? First of all, think about that. And then, by what factor? Remember that the force of gravity is 1 over distance squared. So as the distance goes up, we should keep in mind that the force should go down, but it will go down by a factor of 3 or a factor of 9. The answer is a factor of 9, because the distance is tripling, but if we square the triple, that gives us 9. Now, another question is, for the law of gravity, if we're trying to think of the force between you and the Earth, what do we use for distance? It turns out that Newton figured out that the distance should be measured between you and the center of the Earth. Gravity actually, of course, then exerts a force on you. The force that the Earth exerts on you due to gravity is actually called your weight. And because of that, because you have a force acting on you, you have an acceleration, which is called the acceleration of gravity. For Earth, the acceleration of gravity is 9.8 meters per second squared, which is approximately 10 meters per second squared. This acceleration of gravity is due to the planet's mass and its size, which means that as I move from planet to planet, I will experience different accelerations of gravity, and therefore my weight would actually change. If you are on the moon, what's true about your weight? Well, think about what I just said. When I go to another planet, if I go to the moon, because the moon has a different mass and a different size, and we actually probably know that the force of gravity on the moon is smaller than that on the Earth, our weight would actually decrease. Finally, one last thing that Newton allowed us to explain the motion of the planets had to do with Kepler's second law and the conservation of angular momentum. Angular momentum is the measure of an object's momentum when it travels in a circle. The three things that go into determining angular momentum are its mass, its velocity, and its radius. So here is an object going in a circular path. Because it's moving, it has momentum. Because it's moving in a circle, it has angular momentum. Newton found that as the planets orbited around the sun, they were conserving their angular momentum. And what happened is as their distance from the sun would decrease, because this entire quantity had to stay the same, the speed would have to increase to compensate. It's similar to this example of an ice skater. As she holds her arms out, she has a particular angular momentum which is going to be conserved. That's because nobody's going to push her to speed her up or slow her down. But if she pulls in her mass to a smaller radius to keep her angular momentum constant, she will actually, her rotation rate will speed up. Finally, when we talk about gravity, we have to talk about tides. Because of the fact that the force of gravity between two objects depends on the distance, When we think of the Earth and the Moon exerting gravitational forces on each other, because of the very large size of, say, the Earth, the force of gravity that the Moon exerts on the Earth on the side closest to the Moon is much stronger than the side furthest away. This difference in the gravitational forces at different locations is called what we refer to as either tidal forces or differential gravitational forces, which is sort of a tongue twister. What happens is then the side closest to the Earth bulges out because the force is stronger, and then the side opposite the Moon bulges out because actually the force is weaker. As the Earth rotates underneath these tidal bulges, locations on the Earth experience high tides as they pass under one bulge, low tides as they pass under these more shallow areas. That's how the tides actually occur. We also see that there's a smaller contribution from the sun, and when the sun reinforces the bulge that the Moon is causing, the high tides become especially high, the low tides become especially low, and we call these spring tides. Notice this will happen during full moon or new moon. If the force of the sun actually is at a right angle to the force of the Moon, it tends to sort of cancel out the bulge, and you notice that the bulge difference is not as large here. We call these neap tides, and these will occur at first quarter or third quarter.